All right, welcome to the Mathematics of Data Models, Lecture 10, CS 2810. This is a Northeastern University course, and today we're going to talk about the concept of eigendecomposition. So, we previously learned how to use norms, right? Norms to measure the size of vectors. And we learned the 1 to infinity norm, and the general one is called P norm. Now, today, we're going to look into matrices. How do we measure the size of a matrix, right? So one of the two, there are more than two ways, but two basic ways is one is called a Frobenius norm, and the second one is called a determinant. Okay, so the determinant, both of them will give you a number. This will give you a number. This will give you a number, and it's a way of measuring the size of the matrix. Now, Frobenius norm is very simple. It's essentially the extension of L2 norm. We previously learned L2 norm, which if you have 1 and 2, you just take 1 square, 2 square, and square root the whole thing. Well, the Frobenius norm, you just take every element in here, take the square, and take the square root. So the Frobenius norm is an extension of the L2 norm. So here, for example, right, 1, 2, 1, 3, 1, 2, 1, 3. Everything else is 0. So take the square of them and then take the square root, and that's how we find the Frobenius norm. Now the symbol for the other one is called determinant. That's the other way we're going to learn today. And the symbol for determinant is the absolute value sign. So the absolute value sign for a matrix is specific to the determinant. Now, given a 2 by 2 and a 3 by 3, the equation to find a determinant is essentially you take this, multiply by this, which is right here, subtract this times this. The uh, when I was taught this, they said to picture like a backward alpha. Right? You take this and you subtract the second one. So that's it. This is the equation for determinant. Now, for a 3 by 3 matrix, oh, wait, one more second. For a 2 by 2, you can also picture as this times this, and then this times this, which is exactly what I said, but you'll see why I mentioned this. Now, for determinant of 3 by 3, right, the way it works is you take this and then multiply by the determinant of this square. Since we know how to do 2 by 2, right, this is the determinant. So this is why I mentioned this previously. You take this and you actually multiply by the determinant of this. But since this is just a number, then you just multiply by this number. Now, for 3 by 3, you take this, multiply by the determinant, and then you take this, and then you multiply by the determinant of this. See? I combine it to do two columns. So this second one is subtraction. And the third one is you take this, and then you multiply by the determinant of this corner. And that's it. That's the equation. That's the equation for 2 and 3. Now, matrices bigger than 3 by 3 it just gets more and more and more complicated, right? So we rarely calculate things that's bigger than 3 by 3 by hand. So it's important that you know how to do this, like with NumPy. But you should at least know 2 by 2 and 3 by 3. And knowing the determinant is 0, right? If the determinant is equal to 0 of a matrix, it actually tells us a lot of information about matrix A. For example, if we know that the determinant of A is 0, then we know that there's no unique solution. So unique solution is not possible. The matrix is automatically singular, right? And inverse of A doesn't exist. Tells us the column vectors are linearly dependent. So this was one single test that can essentially tell us a lot of information. Now, For smaller matrices, it's easier to just solve the determinant than performing Gaussian elimination. Therefore, if you're trying to run some of these tests, the determinant might be an easier way to go. Now, you want to pause the video, see if you can calculate the determinant for these two matrices. Now, remember, this right here is the equation for it. Okay, I'm going to go on. So pause the video, try it, and I will continue. Here is essentially showing you how to do it. Like you can step through this. It's the symbol for determinant is like this absolute value, but sometimes you'll also just see det for determinant. So step through this. This is for the second matrix. We also give you the solution, so you can step through it, make sure you understand how to calculate it. So now we move on. Previously, we saw that matrix transformation transforms. So matrix can transform vectors. So if a vector matrix can do something to it, such as rotation, translation, moving to a center. So matrix can do a lot of things, right? So these are some of the things we've thought about. And these transformations essentially allows us to think of X and A like numbers. Like you have this number, you plug it in, it does something to it. Now, these transformations that we are talking about is from the matrix perspective. Is from the vector's perspective. So something is being done to the vector. Now we're gonna change and start looking at it from the matrix perspective. From a matrix perspective, right? What special numbers and vectors are out there? So given some vector, there are a bunch of matrices, like the one that's projection matrix, rotation matrix, right? So from the vector's perspective, there's special matrix that is special to the vector. From the matrix perspective, there are also vectors and numbers. The numbers we normally use lambda to represent them. So there are numbers and vectors, and these are called eigenvectors and eigenvalues. They're not just any vectors, they're eigenvectors and eigenvalues. And they're very, very special in linear algebra. So eigenvectors and values are really special. So far, we learned the concept of independence, right? If a set of bases is independent, that's telling you there are no redundancies. And if they're dependent, it means there are redundancies. The existence of redundancy, right? Existence of redundancy is essentially what allows us to do data compression. Eigenvectors and values essentially allows us to identify the minimum set of vectors that spans the same rank. Okay, so if we have a bunch of vectors, we don't know which one are redundant, but once we find the eigenvalues and eigenvectors, we know exactly what orthonormal basis, the minimum orthonormal basis that spans the necessary space. So, for example, if you were to go, like I haven't taught you how to find eigenvalues and eigenvectors yet, but if you were to find them, what will happen is, for example, you can start with 100 basis vectors. Once you identify the eigenvectors and its associated eigenvalues, then you might get something like this. Here's V1 is the first eigenvector, and its associated eigenvalue is 0.5. V2 is another one, its associated value is 3. V3, V4, so on and so forth. But notice, after V4, V5, V6, V7, all the way to V100 to 100 are 0. So, what is the meaning of the vector and its associated eigenvalue? Well, the meaning is eigenvalues associated with the eigenvector. So these numbers tells you the size of the vector, right? Contributing to the span. So if you have a big number, that means this vector, this direction is really contributing to the span. Whereas this one, which is a much smaller number, is not contributing to the span very much. And therefore, These ones where it's contributing 0, they're essentially redundant. So these are all redundant. Therefore, out of 100 basis vectors, we were able to identify the 4 minimum orthonormal basis, or orthonormal basis. Okay, so this is why knowing the eigenvalues and eigenvectors is really useful. From the previous example, we see that v1 and 4, right? They all contribute to the rank, so they all contribute, whereas these ones, they don't contribute, right? So from 5 to 100, right, they're not really contributing. From this, we can conclude that the rank, right, the rank, the dimension span by this set of 100 basis vectors is really just 4. And there's 96 dimensions that's really redundant, and it's not really contributing to anything. Moreover, if you look at it carefully at V4, it contributes very, very little. So this is doing basically nothing, right? It's contribute very little. Therefore, if we remove V4, if we don't even do this one, then the span is really not going to change that much. So this implies that for any, we really only really care about the largest contributors, and the other ones, they they could be treated as just noise. Like sometimes noise can give you just very, very tiny variations. Okay, so in conclusion, eigenvalues and eigenvectors give us the minimum independent orthonormal basis that spans the same space. Okay, eigenvalues and eigenvectors. Given a matrix A, the eigenvectors of A are vectors that treats A as a number. So, this is the definition. Like, this is very, very important. If you have, why is an eigenvector special? It's special because when you take a vector and multiply by a matrix, it treats this matrix as if it's just a number. Let me explain to you what I mean by that. So over here, this happens to be an eigenvector. Okay. Now, if I were to multiply by this, by the matrix A, notice this is equivalent to the eigenvector multiplied by some number. So if you calculate this out, you will see that they are actually equal. Therefore, the matrix, according to this vector, could be treated as just a number. Here's another eigenvector. Notice that if I multiply by this, it's equivalent to just some number. So this right here is the eigenvector, is the vector such that treats a matrix as if it's just a number. And its associated number is the eigenvalue. So the eigenvalue and eigenvector. That's what these means. Okay? So V1, V2 are special to A because they treat A as a constant multiplier of either 1 or 3. So like I said, then these vectors are called eigenvectors. Therefore, the definition eigenvalues and eigenvectors is therefore a vector such that when you multiply by A, it's equivalent to some number lambda multiplied by V. Okay, so the vector multiplied by matrix is like the vector multiplying by just some value. So our goal today is to learn how to find them. So let's learn how to find them. How do we find eigenvalues? Well, all we have to do really is to start with the definition, which is this. This is the definition. Once we have the definition, well, we can move this to the other side. Therefore, AV times lambda identity V is equal to 0. Now, since this result is in a matrix, what does it mean that the size of the matrix is 0, right? This right here is a matrix. So when that equals to 0, what does it mean? Well, we just talked about size. We know exactly how to measure the size, and the size is the determinant. Therefore, if the determinant is equal to 0, here I put the determinant, then that's how we can view the size. And let's say we have this matrix A. Therefore, the way you will write this is here's A minus lambda identity times V. A minus lambda identity times V. Notice I pulled the V vector out. So this would have distributed. Now, the so what's happening is we're going to we wanted to talk about the matrix. We want the matrix size to be 0. Therefore, what's happening is that we have A V minus lambda I V. We want that to be 0. And then we have A minus lambda I times V is equal to 0. And we want, so here is the matrix. So what happened is we want this to be 0. So the determinant of A minus lambda I should equal to 0. So that came from this, right? From this relationship. And that's what I have and up here. We want the determinant of the matrix minus, so notice the determinant, the matrix minus lambda times identity is equal to this. So now we could calculate the determinant. The determinant is just the inverse alpha I told you about. So this times this, which is right here, minus this times this, which is right here. Okay? So now we have expression. This expression is equal to 0. And we now know how to solve this. This expression here has a special name called characteristic polynomial. Now, the eigenvalues, therefore, is the solution to the characteristic polynomial. And in this case, the eigenvalues will be A11 and A22, right? So that would be the eigenvalue. Now, let's consider this matrix, and let's see if we can do it together. Well, first thing we do is we want the determinant of A minus lambda I to equal to 0. Okay, so A minus lambda I is this minus lambda and this minus lambda. Okay, because this 2, 1, 1, 2 minus lambda, lambda, 0, 0. Right? That's how I got this. Okay, so now we obtain the characteristic polynomial, which we multiply like this. And this leads us to simplify it to this. And if we now pull out the terms, then we can split this polynomial into this. So the solution is easy. The lambda 1 is equal to 3, and lambda 2 is equal to 1. Right? So now we know all the eigenvalues. So it tells us the first eigenvector is contributing 3, the second eigenvector is contributing 1. Now, once we have the eigenvalues, that allows us to solve for the eigenvectors. All we have to do is essentially plug it back in. So let's do the first one where let's do lambda equals to 1. Now, what happens? Well, we see that if we plug 1 here, then we end up getting this. And when you multiply by v, we want that to be 0, right? So if this is equal to 0, how do we solve for the solution for this? Well, this is the null space. This is the null space of the matrix. And the null space, after you do the reduced row echelon form, will look like this. This implies that v1, v2 times this is equal to 0. And therefore, v1 plus v2 is equal to 0, or v1 is equal to minus v2. Now we can now represent the solution where v1 is minus v2 and v2 is v2. So at this step, remember, we are letting the representing all the pivot variable with the free variable. And v1 is a pivot or leading variable. v2 is a free variable. Okay. After this, it's essentially -1, 1 times v2. So this space is then the null space. And also, this is therefore the eigenvector corresponding to 1. So what it's saying, this is the eigenvector. Therefore, if we have -1 times 1, it's going to be 1 times -1, 1. We actually saw this exact same example previously. Okay, now in the second case, where lambda is equal to 3, we can follow the exact same procedure. The step-by-step procedures are here. And you will, at the end, find that the solution eigenvector associated with 3 is 1, 1. And you can see this, right? If I take 1, 1, 1, 1, it should equal to 3 times 1, 1. So take a look how this is actually equal to 3, 3, which is equal to 3 times 1, 1. Therefore, this checks out. Well, of course, we just double check our work. To double check your work, you take the vector, eigenvector, and multiply it. If you multiply it, it should be equivalent to the eigenvalue times the eigenvector. Equivalence here, multiply it, it should be equal to it. And both statements are true. Now that we have the eigenvalues and its associated eigenvector. Eigenvalues associate eigenvector, right? Normally, we like to sort them from the largest to the smallest because we care about the ones that has the largest contribution. And we can organize the eigenvectors as the columns of a matrix, which we call V, right? However, notice that V1 and V2 are not really solutions yet, right? They're not the solutions we want because they're orthogonal, but they're not orthonormal. So for us to finalize the last step, right, what you want to do is you want to normalize both of them and then put them back in. So this right here represents the eigenvectors. Some interesting facts about eigenvectors. Well, the matrix used for finding the eigenvectors must be a square matrix. So in order for us, the A matrix, this has to be a square matrix. Eigenvectors are always orthogonal to each other. In fact, they're orthonormal. Therefore, if we have 3 eigenvectors, the dot product between all of them should be 0. This also implies that they're linearly independent because every one of them, right, that you're looking at, as long as the lambda is not 0, is contributing to the span. And if they're linearly independent, it means that for this equation, you must only have trivial. We also previously learned that having orthonormal bases are very useful for projection. Therefore, eigenvectors is a common way to find the orthonormal basis. Now, eigenvectors and eigenvalues is really a combination of a lot of ideas that we have done so far. First, you need to know the definition, right? So eigenvector is multiplied by matrix is equivalent to the eigenvector multiplied by some number. And then you need to understand the definition of determinant. Then how do you calculate determinant and obtain the characteristic polynomial, right? So you need to understand characteristic polynomial. And then you need to understand the concept of null space. Because once you calculated the characteristic polynomial and get the eigenvalues, you then need to calculate eigenvector. And the eigenvector is therefore when A times lambda I V is equal to 0. Therefore, it's a null space of this matrix. And lastly, you also need to know how to normalize a vector, right? Once you get eigenvectors, that's not good enough. We want orthonormal bases. Therefore, you need to normalize them. So, pause the video, try again. Let's see if you can find eigenvalues and eigenvectors given this. Okay, pause the video. Now, over here, I will give you the step-by-step process is given to you of how you can find it. Okay, so when you're home, pause the video, go to the slide, and see if you can get to it. To find that, so yes, this is also part of it. So this is telling you how to get the eigenvectors. So go through this as well. Now, I mentioned previously that eigendecomposition really only works on square matrices. In fact, it has to be square and symmetric. Symmetric. So if it's not symmetric, you can still find eigenvalues and eigenvectors, but you can't perform this thing called eigendecomposition. Let me see. Nope, I actually haven't got to it yet. Yes, let me talk about this first. Now, eigenvalues and eigenvectors in NumPy. In NumPy, instead of trying to solve each one of them separately, NumPy can just get basically everything at once with a command called ag. So what it returns, right, is that it will return the lambda value. So notice linear algebra, I'm going to call ag. When I call ag of the matrix A, it returns two things, lambda as well as the vector V. Not the vector, the matrix V. So this V, each columns of V is the eigenvector, okay, the columns. And the way they're associated is that the first eigenvalue is associated with the first eigenvector, and the second one, and so on and so forth. Okay. Now, once we have identified the eigenvalues, right, all of them, it tells us the orthonormal basis that contribute to the span. So maybe only first two contribute, and the rest of them are zero, and therefore you only really care about the first two of them. So over here you can see the linear algebra. We previously solved it, which was 3, 1, and we confirm programmatically that the eigenvalues are indeed 3, 1, and these are the eigenvectors. Now, I was mentioning previously that when A is symmetric, under special cases where A is symmetric, which means A is equal to A transpose, the matrix can be decomposed into three matrices. So we just learned lambda, right? So V is the eigenvector matrix. So each column is the eigenvector. Okay, and sigma is a diagonal matrix where the diagonals are the eigenvalues. Remember that the eigenvalues are 3 and 1. So what I'm saying here is if A happens to be symmetric, then A can be decomposed into three matrices. We know what V is. And sigma is the eigenvalues. So if we write this out, here's V, here's sigma, and here's V transpose. If you were to multiply the three matrices together, it allows you to actually reconstruct the original, which means the original can be decomposed into three separate matrices, or that you can view as three separate matrices can come back and form a matrix. So over here, I didn't. This shows you that how we got the eigenvalues and eigenvectors. And over here, notice if I do V dot, the NP diag that turns into lambda 1, lambda 2 into lambda 1, lambda 2. Okay, so that's what diag means. So V times diag times dot V transpose. Notice how this gives us the original matrix back. Okay, so let me go back. I said that when you're trying to do eigen decomposition is when A is equal to V sigma V transpose, right? And this only works on square and symmetric matrix. Symmetric. This is a major drawback, right? This is a major drawback since most data are not square and might not be symmetric. So, so this is a problem. Even though eigen decomposition is really, really useful, it seems on the surface that you can't use it on most data because most data are not perfectly square and they're not symmetric. But it's actually okay. It is okay because you can always turn a non-square matrix into a square matrix by multiplying it by itself transpose. So A can turn into a square if you do A transpose A or A transpose. Right? Both options will turn your matrix into a square. Now you might be thinking, like, but then we are no longer finding the eigenvalues and eigenvectors of A anymore. Right? We are finding the eigenvalues for A transpose or A transpose A, depending on how you're doing it. And that would be correct. However, we are not we're not really, the goal was never to specifically focus on the eigenvectors and eigenvalues of A. The goal for us to identify the minimum set of bases that spans the same span as the column space of A. So as long as we got an orthonormal basis that can span the column space of A, that's all we really care. And we discovered that essentially the orthonormal basis generated by A transpose has the identical span. And therefore now, even if the data is not perfectly square, you could just multiply, make it square, and still able to find the orthonormal basis that you need. This is why, we can generate appropriate orthonormal basis with this instead of and the eigenvectors will span the same space anyways. So a little bit more Python code. If you want to find the Frobenius norm, which we talked about in the beginning, it's just norm with fro. Okay. To calculate a determinant, it's just det of A. And the rest of the eigen values, we already talked about it. All right, to finalize today's lecture, see if you can find the eigenvalues and eigenvectors for this. And this one, if you were to do the eigen decomposition, because it's not symmetric, A will not equal to V sigma V transpose. But since this one is symmetric, B will equal to V sigma V transpose. Okay? And once you have done this, give a bigger matrix a try. This one. I think on the exam, I will have to do one 3x3 because 3x3 allows us to test a lot of various concepts simultaneously. So, yeah, give these a try. And I even provide some of the solution for you. So, good luck. I will see you in the next video.